Hi student, in the last video we discussed that Joule-Thomson effect and the Joule-Thomson experiment. In this class, let us discuss Joule-Thomson coefficient. Already we discussed that the Joule-Thomson coefficient, it is also called as Joule's Kelvin coefficient. Joule-Thomson coefficient is also called as Joule-Kelvin coefficient. So we discussed by using the porous plug last class, a Joule-Thomson effect and its experiment. Based on that, let P1 and V1 and P2 V2 be the pressure and the volume of the gas on the two sides of the porous plug. So we discussed there a porous plug. Here it is a porous plug which contains two brass discs. So here a P1 we took, and here it is a P2, and the volume V1 and V2 be the pressure and volume of the gas on the two sides of that porous plugs. And we discussed that work is done in the expense of internal energy. Let U1 and U2 be the internal energy of the incoming and outgoing gas. Incoming gas and this one is outgoing gas. Here U1 and U2 be the internal energy. So the net work done by the gas on the piston is W is equal to, this can be written as P2 into dV2. So a small volume, integration of P1 into dV1. If you simplify this one, we are going to get W is equal to P2V2 minus of P1V1. Let us consider this one as an equation number 1. So we know that heat neither enters to the system and nor leaves from the system. Therefore, the work has to be done at the expense of internal energy. So U1 minus of U2 is equal to P2V2 minus of P1V1. Therefore, U1 plus P1V1 is equal to U2 plus P2V2. This can be written as H1 is equal to H2 because H is nothing but enthalpy, that is equal to that the sum of the internal energy and the product of pressure and volume, where H is an enthalpy and this enthalpy remains constant here. And the next one is, if the enthalpy is a function of temperature and pressure. Therefore, enthalpy is a function of temperature and pressure, that can be written as H is equal to H of T, P. If we differentiate this one, we are going to get dH is equal to dou H divided by dou T of P into dt plus of dou H divided by dou P of T into dP. So let us consider this one equation number 2 and this represents equation number 3. Now dH is equal to dou H divided by dou T of P in the sense Cp into dt plus of dou H divided by dou P of T into dP. Let us consider this one as an equation number 4. Here Cp in the sense dou H divided by dou T of P we are going to get. Let us consider H is equal to U plus of PV. Now differentiate above expression, we are going to get dH is equal to du plus of P into dV plus V into dP. So here are the two terms. By product rule we have to apply for the differentiation. Here du plus P into dV in the sense dH is equal to dQ plus of V into dP we are going to get. Here dH that can also written as TdS plus of V into dP. So because we know from the first law of thermodynamics, dQ is equal to du plus of P into dV, and in a second law of thermodynamics dQ is equal to T into ds. Therefore we are going to get this expression dH is equal to TdS plus V into dP. Now this can also written as dou H divided by dou P of T is equal to T into dou S divided by dou P of T plus of V. Equation number 5 we are going to get. So differentiate with respect to P at a constant temperature. If we differentiate with respect to P at a constant temperature, we are going to get this expression, that is dou H divided by dou P of T is equal to T into dou S divided by dou P of T plus of V. From Maxwell's equation, dou S divided by dou P of T, dou S divided by dou P of T is equal to minus of dou V divided by dou T of P. Let us consider this one as equation number 6. Already we know this expression from Maxwell's equation. Now substituting equation 5, so we get dou H, substituting in equation 5 we get dou H divided by dou P of T is equal to minus of T into dou V divided by dou T of P plus of V. Here dou S divided by dou P of T, that can be written as dou V divided by dou T of P. Therefore we are going to get this expression. Let us consider this one in equation number 7. Substituting equation 7 in equation 4. We know that expression for equation 4 that can be represented by dH is equal to Cp into dt, dou H divided by dou P, dou T into dP. So we know here an expression that is dou H divided by dou P of T. If we substitute, we are going to get an expression that is dH is equal to Cp into dt plus of V minus of T into dou V divided by dou T of P into dP. Let us consider this one as an equation number 8. Since Joule-Thomson expansion or experiment is an isoenthalpic, therefore dH is equal to 0. Now dH is equal to 0, the above expression we are going to get Cp into dt plus of V minus of T dou V divided by dou T of P into dP. We are going to get Cp into dt, which is equal to T dou V divided by dou T of P minus of V. So we are going to get dP. Therefore, dou T divided by dou P of H is equal to 1 divided by Cp into T dou V divided by dou T of P minus of V. Let us consider this one as an equation number 9 we are going to get. Now, dou T divided by dou P of H in the sense mu, which is equal to, so if we simplify this one, T square divided by Cp dou divided by dou T of V divided by T of P we are going to get, and this finally this can be written as T square divided by Cp dou divided by dou T V divided by T of P, equation number 10. So this represents the Joule-Thomson coefficient. This is a Joule-Thomson coefficient that can be defined as, definition for Joule-Thomson coefficient, the quantity is a measure of the change in temperature per unit change of a pressure at a constant enthalpy. And this is about Joule-Thomson coefficient. And here they explain some values of a Joule-Thomson coefficient. That is, we can consider those are cases. In that first one, so first case explains that if mu is a positive, so mu is a positive when dt will be dt is a negative. At that time the process takes place. Cooling will be produced. Second case, if mu is negative, that implies heating effect. Mu is negative, dt is a positive, therefore it implies heating effect. Here it is cooling and here it is heating. And the third case, explain, if mu is equal to 0, this implies no heating and no cooling process takes place. Right? And these are the three cases they explain in Joule-Thomson coefficient. Thank you.